Hello students, we're going to start discussing a new topic which is differential equations. So we will of course use the ideas that we developed in terms of eigenfunction expansions, Fourier series, Fourier transforms and Laplace transforms as we go along. But the first lecture or so will be somewhat introductory and elementary, and many of you may know some of the basics that I'm going to discuss in this module, but for the benefit of everyone and for the sake of completeness, I thought I'll give a very general introduction to differential equations and then move on to solution techniques. Okay, so differential equations are everywhere when you want to describe rate processes like heat transfer or fluid flow or mass transfer or reaction kinetics and so on. So some of the famous equations that we solve to understand fluid flow phenomena, such as the Navier-Stokes equations, the Fourier's law of conduction, the unsteady heat equation. They are all differential equations. Okay, so a differential equation is basically, in one of the simplest examples, it is a relation between the derivatives of the function and the function, perhaps the function itself, right, and some other known functions. Okay, so here y of x is called the dependent variable because that is the function which you are trying to solve, and x is called the independent variable. Okay, so this is a relation connecting the second derivative of y with the square of the first derivative of y and a known function. So whichever function y of x that satisfies this is a solution to this equation. Like in the case of ordinary algebraic equations, suppose I have x plus 3 is 0, you know that x is equal to minus 3. This is a linear equation in one variable. Okay, there is only one solution. But you have quadratic or cubic equation, you have more than one solutions. In the same way, linear differential equations have unique solutions, whereas nonlinear differential equations can have many solutions or no solutions. There is no single answer to that. Okay, now I want to make some distinctions between various types of differential equations. First is ordinary differential equations versus partial differential equations. The equation that I just wrote down here is an example of an ODE, because you just have only one independent variable. ODEs are characterized by only one independent variable, x or t. So for example, the unknown function y is a function only of x. Okay, this is an example of ODE. Okay, whereas in PDE, the unknown function is a function of more than one variables, let's say x and t. For example, the unsteady heat equation is given like this in one spatial dimension. Of course, you can have more than one spatial dimension. This is in one spatial dimension. In three spatial dimensions, this will take the form is equal to alpha t times partial squared t by partial x squared plus partial squared t by partial y squared plus partial squared t by partial z squared, right? So here t is a function of x, y, z and t. It's a function of four variables, the three spatial coordinates and one time variable, right? So these are examples of partial differential equations, PDEs in short, and ordinary differential equations are usually shortened as ODEs. Okay, right, we will discuss both PDEs and ODEs. This is one set of classification. Obviously the Navier-Stokes equations are partial differential equations. Now the next category that I would like you to understand is linear versus nonlinear differential equations. Now linear, the general notion of linearity is, of course, if I have an operator, if I operate it on some constant times some function phi1 plus some other constant times some other function phi2, this can be written as alpha 1 times L phi1 plus alpha 2 times L phi 2. Suppose I take L as d squared dx squared, you can easily verify that this is indeed the case. So this is an example of a linear operator. Okay, suppose L is d by dx the whole squared, then this will not be, this is definition of linearity. Okay, now if I take this is not a linear operator, so it's a nonlinear operator. Okay, in the same way you can categorize differential equations as linear versus nonlinear. Suppose I have d to the 4 y by dx to the 4 plus d squared y by dx squared minus y of x is equal to exponential of minus x. Okay, now here each operator is linear because the unknown appears only once, unknown or its derivative appears only once. So this is a linear operator. Now the right side has e to the minus x. E to the minus x is a nonlinear function of x, but x is a independent variable. It's known. So linearity or nonlinearity is decided only based on whether your unknown function or the dependent variable occurs linearly or non-linearly. Okay, and so anything that is not linear is non-linear. So for example, non-linear differential equations, ordinary differential equations can appear like this: dy by dx to the power 4 plus d squared y by dx squared is 0 or something like that. So here, sorry about this, here you have the derivative appearing to the power 4, so it's non-linear, right? And you could also have d power 4 by dy dx to the 4 plus sine y is 0. So sine y is a nonlinear function of y. This is again an example of a nonlinear ODE. It's an ODE because you have only ordinary derivatives. Of course you could have nonlinear PDEs as well, as in the case of Navier-Stokes equations. So anything that is not linear is nonlinear, and the fundamental way you check whether something is linear or nonlinear is to use the basic criteria of linearity as shown in this expression. Okay, now the third distinction I want you to very well understand is dependent variable versus independent variable. Dependent variables are the ones that are unknown, that let's say temperature as a function of x, y, z, time. T is the dependent variable, whereas the spatial coordinates and time are the independent variables. Okay, this is something that you should understand, because this is what will help you to judge whether a differential equation is linear or non-linear. Because as I just showed you here, you may have an equation that is non-linear in the independent variable x, but the equation still remains linear because this is just non-linear in the independent variable. So you have to understand this very clearly, right? Now the other thing that I would like you to understand is what is called an order of an ODE or a PDE. Okay, this is the order of the highest derivative that the equation contains. The order of the highest derivative the differential equation contains or has. For example, if I have plus is equal to sine x, okay, now you have to look at only the order of the derivative. The highest order is 3. Here the first derivative is raised to the power 4. This is not the order. This is the order, is 3. This is a third order differential equation. Now this is called the degree. This is not the order. The highest power to which a derivative is raised, okay, the highest power to which the highest order equation, highest order derivative is raised, okay, that is called the degree. So this is still third order, okay, of first degree. Okay, suppose I have d squared y by dx squared the whole square is 0, this would be still order, this is second order, and this will be still second degree, and you don't worry about this. This is the power of a lower derivative, so you do not base the degree of the differential equation on a lower derivatives. Okay, now let's understand some basic notions in the solution of a differential equation. Let's say you have d squared y by dx squared is 0. If you solve this, if you integrate this once, you will say dy by dx is some constant. If you integrate this once more, then you will say y of x is c1x plus c2. So by solving this differential equation, that is by integrating, you pick up two constants of integration here. C1 and C2. Okay, so in general, when you solve a differential equation, you will pick up constants of integration, and these have to be fixed using physical constraints called initial or fixed using physical constraints called initial conditions, ICs in short, or boundary conditions, BCs in short. Okay, so depending on the nature of the problem, you will fix these using either initial conditions or boundary conditions. Okay, so such a solution is called, this solution where the constants are not fixed is called the general solution. So the general solution of a differential equation contains constants of integration, and these are fixed subsequently using boundary conditions or initial conditions. Okay, all right. So now the next idea that you have to understand is initial value problem versus boundary value problem. Initial value problems are denoted as IVP. This is denoted as BVP. Okay, so suppose I say that mass times the acceleration of a particle is the force on the body. In order to solve this is a differential equation in time. You have to specify the position of the particle at time t equal to 0 and the velocity of the particle at time t. This is Newton's law of motion, right? You have to specify two conditions. This is an initial value problem because you cannot specify the in general, physically speaking, you cannot specify the position of the particle at some other time. You typically say that I have a particle at time t equal to 0 at this position and with this velocity. Now let us find out what is the trajectory of this particle at later times. Okay, such problems are called initial value problems. Okay, this is an example of an initial value problem. And how many these are called initial conditions. How many initial conditions you need to supply? That depends on the order of the differential equation. If you have a second order differential equation, you need 2 initial conditions. If you have a third order, you need 3, and so on. Now in contrast, suppose I say that the temperature in a bar is given by some function of x. Now the bar, it's just 1D conduction, let's say this is x, so you have to specify the value of temperature at x equal to 0 and x equal to L, and these are called boundary conditions. The temperature or the value of its derivative at both the boundaries will be prescribed by the physical formulation of the problem. Okay, now so the general solution of an nth order ODE will have n constants of integration. I showed you an example where second order ODE, upon integrating twice, gave 2 constants of integration. You need, for a general solution of nth order ODE, you have n constants of integration that need to be fixed by the appropriate use of initial conditions or boundary conditions depending on the context of the problem. Once these are fixed, the solution that one obtains is called the particular solution. Okay, once the general solution is fixed, the constants in the general solutions are fixed using boundary conditions or initial conditions, you get what is called the particular solution. Okay, now let's consider one of the simplest ordinary differential equations. These are linear ODEs of first order. This is something that we encounter in process control. So you have y is the dependent variable, x is the independent variable, plus p of x y is equal to q of x. Okay, now p of x and q of x are known functions of x. These are given to us. Now, how do you solve this equation? You multiply this equation by what is called an integrating factor, such that integrating factor is denoted as mu of x. So let's first multiply mu of x dy by dx plus mu of x p of x y. Okay, this is the left side. This is equal to q of x mu of x. Okay, now if you look at this, this is nothing but okay. Now I want to be able to write, I have not found, I don't know what is mu of x yet. I want to be able to write this as d dx of mu of x times y is q of x times mu of x. Okay, so what I want is, if I expand this, d dx mu dy by dx plus y d mu by dx should be the same as this one, mu dy by dx plus mu p y. Now if I cancel this out, I get y d mu by dx is mu p. Now the y will get cancelled, so d mu by dx is mu p. This implies this. So if I integrate this, mu of x is e to the integral p of x dx. Okay, so once mu of x is found, I can substitute it here, then I can integrate this because this is easy to integrate. So this is called the integrating factor. So this one becomes, if I integrate this once, I get mu of x times y is integral mu of x prime q of x prime dx prime. So you typically don't use the same dependent because this is getting integrated over, right? So I should not use, so this is integrated from any value of x, let's say some a to current value, x prime is equal to a to x prime is equal to x, where x prime is the integrated variable and x is the variable that you're specifying here. Okay, so this is the solution of this equation. So where mu of x is given by, this is the integrating factor, it's e to the integral p of x dx. Okay, so this is something that we encounter many times in process control. This is one of the simplest equations that has an analytical solution. Okay, so let's do an example. Let's say you have dy by dx plus 2xy, sorry about this, is equal to 4x. Okay, now the integrating factor, of course, is mu of x is exponential e to, see, this is dy by dx plus p of x is 2x, q of x is 4x. So integrating factor is y e to the integral p dx, it's 2x dx, it's nothing but e to the x squared, right? So y from the previous um, expression that we had, y e to the integral p dx, which is y e to the x squared, is equal to integral q. Q is simply 4x e to the integral p dx, e to the x prime squared dx, and then this is integrated from some a to x plus some constant which is fixed by using boundary conditions. So y of x is nothing but, right, if I do this integration, I'll get, so y of e to the x squared y of x is, if I do this integration, so right now I don't know from where I'm doing the integration. That depends on where the initial condition is, or the condition is given to us. So if I do this integration, I'll get 2 e to the x squared plus c, or if I multiply by e to the minus x squared, I'll get y of x is 2 plus c to the minus x squared. Depending on the condition that you have, let's say at x equal to 0, if you know what y is, you can substitute that and find c. Okay, that's how one solves these equations. Okay, now let's move to higher order differential equations. Higher order linear ODEs. Okay, the general structure is of the form a sub n x d to the n by d x to the n. Y is the dependent variable and x is the independent variable. Some known function. Okay, now like in linear system of equations, if f of x is 0, this is called a homogeneous differential equation. If f of x is non-zero, this is called an inhomogeneous differential equation. Okay, now the general solution contains, if I solve by first, let's call this differential equation L y is equal to f. Okay, L is this operator that is just written down here just to save time. I'm writing this as Ly equal to f. First solve the homogeneous problem Ly equal to 0. Okay, you will get what is called the complementary function, which is denoted normally as yc of x. Because you have a nth order differential equation, you will pick up n constants of integration and n solutions. Okay, this is called the complementary solution or the complementary function. Okay, now usually these are linearly independent solutions. This y1 to yn are linearly independent solutions. Y1 are linearly independent. How do we know this, that they are linearly independent? That means if I multiply y1 and y2 by constants cn, this is 0 if and only if all the cn's are zeros. Okay, now how do we know this? Suppose I have this is 1, then I can differentiate this and do it for n minus 1 times. Okay, so if this were to have non-trivial solution, if this has to have only trivial solution, that means the determinant should be non-zero. Of this coefficient matrix should be non-zero. Okay, that is the condition for linearly independent nature of these n solutions. So the general solution to Ly is equal to f is a combination of the complementary solution plus a particular solution or a particular integral. Okay, this is possible because you are talking about linear differential equations. L is a linear operator, linear differential operator. So you can first set f equal to 0, find the solutions, and then you can put on f. You can take the f and then add the consequences. Because the system is linear, you can do this. This is not possible for nonlinear systems. What is yp? It's any solution to Ly is equal to f. Yp is any solution, okay, to this problem. Okay. Now if a n to a naught, these are constant coefficients, that is, they are not functions of x themselves, then you can get solutions that are relatively simple. Okay, and f of x is 0, then you have what is called the homogeneous problem. Okay, so you have a n d to the n y complementary function by dx to the n plus a naught yc equal to 0. So yc upon must have n constants. Okay, and therefore and then n linearly independent solutions. How do you find those solutions? Y is equal to, let y is equal to a to the power lambda x. You get a n lambda n plus a n minus 1 lambda to the n minus 1. This is a trial guess, and then we'll see whether it gives solutions. Okay, this is a polynomial that has n roots for lambda. Okay, in general. Okay, and in some cases the root may be repeated and so on, but in general it has n roots. Okay, now if all roots are distinct of that polynomial, then the n solutions are of the form e to the lambda mx. M goes from 1 to n. These are all linearly independent because all roots are distinct. Okay, so the complementary solution or the complementary function is c1 e to the lambda 1 x plus c2 e to the lambda 2 x plus cn e to the lambda n x. This is the solution. If some roots are complex, then they come in complex conjugate pairs. If alpha plus I beta is a root, then alpha minus I beta is also a root. Okay, so you can always write c1 e to the alpha plus I beta x plus c2 e to the alpha minus I beta x by combining the sines and cosines and so on. You can write this in the form of a e to the alpha x sine beta x plus phi or something like that. Okay, where the constants instead of c1 and c2 you have a and the phase, the amplitude and the phase of this function. Okay, so you could also have a e to the alpha x cos beta x plus phi, where beta is written here. Okay, you know beta from the solution of that equation, polynomial equation. Okay, if some roots are repeated, then if let's say lambda 1 occurs k times and k is greater than 1, then we will not have n linearly independent solutions because some of the lambdas are the same. So in that case you should have x e to the lambda 1 x, x squared e to the lambda 2 x, x to the k minus 1 e to the lambda kx. Okay, these are also solutions. Okay, sorry, lambda 1x, where lambda 1 is the repeated root, it's repeated k times. Okay, now let's do one example. Find the complementary function of Okay, to find the complementary function, RHS must be set to 0. So d squared yc by dx squared minus 2 dyc by dx plus yc is 0. Then I substitute y is equal to e to the lambda x to get lambda squared minus 2 lambda plus 1 is 0, which is lambda minus 1 the whole squared is 0. So lambda is 1 repeated twice. Okay, so if e to the x is one of the solutions, then x e to the x is the other solution. So y complementary becomes c1 plus c2x multiplied by e to the x. Okay, so to find the particular solution where you have to keep the e to the x on the right side as well, this is the complementary solution. There is no single generally applicable method. You have to do a little bit of trial and error, and you have to if the function is of the form e to the x, then you can try y particular also as some e to the lambda x and so on, or e to the x. There is no lambda here. Okay, there is just e to the x, and then try substitute this format in this equation and see whether it satisfies, right, for some value of a or b or something like that. Okay, so there is no single general method for solving the particular integral. There is one method called the method of variation of parameters, which if time permits I will discuss in a future module. But for now I'll stop here. These are some of the simplest differential equations, ordinary differential equations that are linear with constant coefficients. In the next module I'll tell you how we can solve initial value problems using Laplace transform, and then we'll take it from there. Okay, for now I'll stop here, and thank you for your attention.